Hello and welcome to this FP3 paper walkthrough. This is the updated version of the January 2023 paper. It was an hour and a half. You were allowed the formula booklet and a calculator. Jumping straight into question number 1. Given that y is equal to 3x arcsine 2x, determine an expression for the first derivative. Okay, in the formula booklet we are given the derivative of arcsine x as 1 over the square root of 1 minus x squared. So here we can say that dy by dx, differentiating 3x first using the product rule here, we get 3 times the arcsine of 2x plus, leaving the 3x alone, differentiating the arcsine 2x, we get 1 over the square root of 1 minus x squared, but it's not x now, it's 2x. So we get 1 minus 2x squared, and then the 2x here, we need to differentiate that and multiply it. So we get 2 over instead of 1 over. Tidying this up a little bit, we get 3 arcsine 2x plus 6x over the square root of 1 minus 4x squared. Part B, hence determine the exact value of this derivative when x is equal to 1/4. Giving our answer in the form a pi plus b. Okay, so we go ahead and put this in. Get 3 arcsine of 2 times 1/4 is 1/2, plus 6 over 4 times the square root of 1 minus 4 lots of quarter squared, which is a 16th. So 4 over 16, let me write for now. Arcsine of 1/2 is equal to pi by 6. And then here we've got 3 over 2 times the square root of 1 minus 1/4 is 3/4. That simplifies to pi by 2 plus square root of 3. So we compare that with what we've been given, a pi plus b. A is equal to 1/2 and b is equal to square root of 3. That's question 1 finished. On to question 2. A nice straightforward start. Question 2. A hyperbola h has this equation. So straight away we can say b is equal to the root of 5 if we need that, where a is a positive constant. So we know a is greater than 0. The line with equation x equals 4 over 3 is a directrix of h. Write down an equation of the other directrix. Okay, the directrices are plus and minus the same thing, so the other one is minus 4 over 3. Part B, determine the value of a. So we already have an equation from the directrix. The directrix is minus a over e, so that's minus 4 over 3, which tells us that a is equal to 4e over 3. But we need another equation connecting these two, and we know that for a hyperbola, b squared is equal to a squared e squared minus 1. That's in the formula booklet in the conics section. So 5 is equal to a squared. We didn't really want it written like that. What we want is 3a over 4. So that's 9a squared over 16 minus 1, and we have an equation in a to solve. 9a to the 4 over 16 minus a squared minus 5 equals 0. Making that look a little bit nicer, we've got a to the 4 times 9 minus 16 lots of a squared minus 80 equals 0, and this is a quadratic in a squared. I'm not going to bother trying to factorize that, I'm just going to work it in the formula. So we've got 256 minus 4 times a times minus 80, all divided by 18. And my calculator tells me that either equals 4 with a plus root or minus 20 over 9 with the negative root. We can't have this because that will give no real solutions when we try and square root that. Whereas here we've got plus or minus 2, and we know from above that a is positive, therefore a must equal 2. Part B, I finished. I, the coordinates of each of the foci of H. This should be easy now that we know a is equal to 2. We also know e is equal to 3a over 4, which we can now say is 3 over 2. And the foci are plus or minus a, e, 0. Now we know that a, e is equal to 2 times 3 over 2 is a 3. So our two foci are 3, 0 and minus 3, 0. Now keep in mind, if you forget any of these little bits, that this, and this are all given in the formula booklet under the conics section. So they're all given to you. On to question 3. Hyperbolic trig. So we've got 4 tanh x minus sec x is equal to 1. I think it's always good to get it in terms of sinh and cosh. There are a few different ways of doing this one. I'm going to multiply by cosh. And then usually I like to connect sinh and cosh to get rid of one of them so that it's all in sinh or all in cosh, and you could do that by squaring everything and then change your cosh into a sinh by connecting cosh squared and sinh squared through the identity that you've got for that. But if you do it that way, you'll be introducing an extra solution, so you'd have to check your solutions are all valid at the end. With sine and cosine, that's about the only way I would think to do it. But with sinh and cosh, we know the definitions of these in terms of exponentials. So what we can do here is just change them into their exponential definitions. And I think that would be a little bit safer, instead of potentially creating a solution that we don't really want. So we multiply everything by 2, these are effectively bracketed, and expand out. We get 4e to the x minus 4e to the minus x minus 2 minus e to the x plus e to the minus x, nope, minus, I just said it was a bracket. And then collecting the terms, 3e to the x minus 5e to the minus x minus 2, and whenever in a situation like this, multiply everything by e to the x, and you can get a quadratic in e to the x. Let me just write that in its more familiar way. I find it easier to factorize if it's like this. Assume it can, I think it will. Got a 5 and a 1. And to make a 2, we want the 3 in here with the 5. E to the x minus that plus that, yes. Okay, that gives us the solution e to the x is equal to minus 1, or e to the x is equal to 5 over 3. Now in this form, it's obvious to see that this does not give us a solution, because you can't get a value for x that will make e to the power of x equal to minus 1. And over here we can take logs of both sides, and we get x is equal to the natural log of 5 over 3. Giving an answer in the form yes. So k is equal to 5 over 3. And that is the question done. Question 4. Determine the integral of this thing. Now again, if you go back to your formula booklet, there's a bunch of integrals there that are kind of in this form. We've got x squared minus a squared and a root. We've got x squared plus a squared and a root all over 1, all over 1. And there's a bunch of them there. So what we want is to put this in the form x squared plus something squared. And to do that, we'll factorize out a 9. So the square root of 9 times x squared plus 16 over 9. And then we can bring that 9 as a 3 outside of the root. And in fact, I will bring it outside the integral altogether. Having a sneaky peek at the formula booklet there, I can tell you that this is r sin x over a, where a here is 4 over 3, the square root of this bit here. So x over a becomes 3x over 4 plus c. Part B says, hence determine the exact value of this thing from minus 2 to 2, giving your answer in the form this. Okay, I've just said that this is r sin, but don't panic, because in the formula booklet it also gives you the logarithmic version of this. So again, I've just had a quick look at the formula booklet, and here is the alternative version of that, but I'll have to change it slightly because a is 4 over 3. So let me put that in. But x plus the square root of x squared plus a squared 16 over 9. So there's the logarithmic version of the same thing. Now we can evaluate it and get it in the form that they want. So we're going from minus 2 to 2 of 1 over the square root of 9x squared plus 16 is equal to 1 over 3 natural log x plus the square root of x squared plus 16 over 9, evaluated at minus 2 to 2. So that's a natural log of 2 plus the square root of 4 plus 16 over 9 minus a third natural log minus 2 plus, and then because we're squaring that, we'll get 4 plus 16 over 9 again. And we need to tidy this up into one log function. So let's take a third there, and we can then combine the logs because of the minus with our log rules. That can give one log as a fraction, and at the same time I'll tidy up the square root. That gives 52 over 9. So we've got 2 plus the square root of 52 over 9 over minus 2 plus the square root of 52 over 9. And that is 2 plus 2 root 13 over 3 over minus 2 plus 2 root 13 over 3. Bit of manipulation here. Let's change that into 6 plus 2 root 13 minus 6 plus 2 root 13, and then multiply it by 6 plus 2 root 13 over 6 plus 2 root 13 to rationalize the denominator. And because I can bring a power out the front of the log, I'm going to leave that numerator as 6 plus 2 root 13 squared, and hopefully we get a square number on the bottom. That's going to give us 52 minus 36, and it is. That's a 16, so that gives us 1/3 log 6 plus 2 root 13 over 4 all squared, and then that squared can come out the front. 2 over 3 natural log of, I think they wanted it in 2 bits. Yes, let's split our fraction. So we've got 3 over 2 plus 1 over 2 root 13. And then it's a, b, and c. C is square root 13's coefficient. Yes, so a is 2/3, b is 3 over 2, and c is 1/2. Is that the end? Question 4b finished. On to question 5. Matrices. Part A, determine the exact value of little a for which the matrix capital A is singular. Now if it's singular, that means it does not have an inverse, and it does not have an inverse when the determinant of A is equal to 0. So we want this to be true, which means the determinant must equal 0. The determinant of A, keep that at the top of the screen there for a minute, is the first element, A, times by its minor. If I make this a little bit clearer, write the minor out, for 0, A5, minus the second element, which is also A, times its minor, minus A0, 4, 5, plus the third element, 1, times its minor, minus A, 4, 4A. And all of that has to equal 0 if the matrix is going to be singular. So here we've got 20 minus 0, so that's 20a. Here we've got minus 5a minus 0, so that's plus 5a squared. And here we've got minus a squared minus 16 times the 1. So we're solving this. We've got 4a squared plus 20a minus 16, a squared plus 5a minus 4, and we're not going to be able to factorize that. So onto the formula, square root of 25 minus 4 times a times c, all divided by 2. 25 plus 16 is 41. Divided by 2, do we know anything about a? A is a positive constant. Therefore, a is equal to minus 5 plus root 41 over 2. That's not very nice. What does it say? Yes, determine the exact value for a. So I think we're okay. Given that 2 is an eigenvalue of a, determine the value of little a. Now we've just determined the value of a, but it's important to realize that these are two separate situations. We've done part A, that's finished. The matrix A is singular if little a is equal to what we've just found. Now it's changed. Given that 2 is an eigenvalue, there's a different value of little a, and we need to find it again. But we need to find it in a different way because of the information we've been given. We need to find the other two eigenvalues as well. So if we kind of go through the normal way of finding eigenvalues, I think that will be the way to do this question. A normalized eigenvector for eigenvalue 2. Now, it's very tempting to use this to answer part B, but we shouldn't really do that. I don't know if you would lose marks for that, but you shouldn't use information given later in the question. Especially, for example, here to here, the information given later in the question would lead you astray. You would get the wrong answer for part A because it's so separate. But here, I think that normalized eigenvector probably would help us. I would use it perhaps in an exam if I were to get stuck and not know what A is. I could use this to help me as a last resort, because I don't think we really should use that. So I'm not going to use that. Let's do it the way they probably expect us to do it, and that is using the eigenvalue here and going through the normal eigenvalue process. We would still be using the eigenvalue if we were to use this, but I don't think we should. So we're going to need the matrix. Let me write this out and drag it down. Minus A for 0 for A5. So to find our eigenvalues, what we would normally do is find the determinant of a minus lambda I, set that equal to 0. So we've got a minus lambda a1 minus a 4 minus lambda 0 for a 5 minus lambda. The determinant of this must equal 0. That's going to give us an equation in lambda to solve, except what we're actually going to do is put lambda equals 2 in and solve for a. And then once we know a, we'll go back and we'll solve for the other two lambda solutions. Same as we did before with the determinant then, we've got the first element times by its minor. I won't write them all out this time. Let's just do 4 minus lambda times 5 minus lambda, and then that will be minus 0. I won't even write that in. No, I will. Minus 0. And then minus a times 5 minus lambda, and then minus 0 again, plus 1 times minus a times a minus 4 times 4 minus lambda. And all of that has to equal 0. Now we're going to get rid of the big brackets, but I will leave some of it factorized still. I think that'll be easier in the next step if we do it that way. Minus a squared minus 4 lots of 4 minus lambda. Because although we would normally solve for lambda here, what we need to do is put the information lambda equals 2 given in the question to find a. So we've got a minus 2 times 2 times 3 plus a squared times 3 minus a squared minus a 4 times a 2 is 8. That gives us 6a minus 12 plus 3a squared minus 8 is equal to 0. 2a squared plus 6a minus 20. Make it easier to factorize if we divide. And that's going to give us a 5 and a 2 plus 5 minus 2. So a is minus 5, or a is 2. And I think we've got information that a is a positive constant. Now you might say, oh, that's part of the first part of the question, and it kind of looks like it is, but this being even before part A is separate even from that. So this is still true for the rest of the question. So a is a positive constant still for this part. So we've got a equals 2 as our final answer here for a. So that is part I of B. Now we need to find the other two eigenvalues, which is just putting that back into this equation here and then finding lambda. So now that we know a, we've got 2 minus lambda, 4 minus lambda, 5 minus lambda, plus 2 squared, 4, 5 minus lambda, minus 2 squared, minus 4 lots of 4 minus lambda. Now we have the fun of expanding all of this out, collecting it into a cubic equation and solving. 2 minus lambda, 20 minus 9 lambda plus lambda squared, plus 20 minus 4 lambda minus 4 minus 16 plus 4 lambda. Those two cancel, and so do these. Which means I'm not going to continue expanding that. I'm going to refactorize it because that gives us our answers a lot sooner than I expected. That's a 4 minus lambda, and 5 minus lambda gives lambda is equal to 2, the one we already knew. Lambda is equal to 4, lambda is equal to 5. So 4 and 5 are our two new eigenvalues. Part B finished. Now we can use this normalized eigenvector for the eigenvalue 2 as this. Determine a normalized eigenvector for each of the other eigenvalues of A. Now this eigenvector that they've given us isn't going to help us in part C, but I can tell you why it's there, because the updated element of this paper is this question. I had a quick look because I was curious as to why they updated it. The original question 5, you did need to use this eigenvector, so the reason this is given is no longer valid. We didn't need to know that this is an eigenvector in order to find the normalized eigenvectors for the other two. Because to find the eigenvectors, we go back to the matrix. But now we know A, so we've got 2, 2, 1, minus 2, 4, 0, 4, 2, 5. Taking that with us. And this is part C. So we're going to apply that onto the vector x, y, z. Because the whole point of an eigenvector is that it does not change except for a factor, and that factor is the eigenvalue. So let's start with lambda equals 4. So now I can peel off the components one by one. So we've got 2x plus 2 times y plus 1 times z must equal 4x, not particularly helpful. Let's have a look at the next one, minus 2x plus 4y plus 0z is equal to 4y. That's much more helpful because that tells us that x must equal 0. And the last one, 4x plus 2y plus 5z is equal to 4z. Now if we know that x must equal 0, that is telling us that z is equal to minus 2y. And if x must equal 0, the first one is giving us the same information. Z is equal to minus 2y. So if we let y is equal to 1, then z is equal to minus 2, and x we know must be 0. So we get 0, 1, minus 2, but don't stop there because that's not normalized yet. So the normalized eigenvector, we need to divide it by the magnitude. 1 squared plus 2 squared is 5. So we get 0, 1 over the square root of 5, minus 2 over the square root of 5. And that is our answer for lambda equals 4. I have to do the same thing all over again for lambda equals 5. So it's the same matrix, obviously. We're still using x, y, z, but this one will give us 5 times x, y, z. So we've got 2x plus 2y plus z equals 5x minus 2x plus 4y plus 0z equals 5y. Not as useful, but still okay. Y is equal to minus 2x. And then the last one, 4x plus 2y plus 5z must equal 5z. Now be careful, that is not telling you that z equals 0. It's just cancelling out and is telling us that 2y equals minus 4x. So that's giving us the same information as the second one. So we're going to put this information back into the first one to see the relationship with z. So if y equals minus 2x, 2y is minus 4x plus z, 5x, and we still have the 2x there. So z is equal to 7x. So we know y and z in terms of x, so let's say x is a 1. Then y is equal to minus 2, and z is equal to 7. Again, that gives us a vector, but not the normalized vector. 7 squared plus 2 squared plus 1 squared is 54. So we've got 1 over the square root of 54, minus 2 over the square root of 54, and 7 over the square root of 54. And that is the normalized eigenvector for lambda equals 5. That, I think, is the question finished. Yes. On to question 6. Oh, too far. Oh, I got onto the last page of working there. Don't often do that. Question 6. A curve has parametric equations. Here they are, where a is a positive constant, getting a lot of positive a constants here. Show that this is true, where k is a constant to be determined. Okay, to show this, we are going to need to differentiate each of these with respect to theta. So if x is equal to, I'll expand that out, a theta minus a sine theta, then dx by d theta is equal to a minus a cos theta. Y is equal to a minus a cos theta. So dy by d theta is equal to a sine theta. Now we square them both, add them together, and probably do some manipulation because there's a theta over 2 there, and we've got thetas. So dx by d theta squared plus dy by d theta squared is equal to a minus a cos theta squared plus a squared sine squared theta. That gives us a squared minus 2 lots of a squared cos theta plus a squared cos squared theta plus a squared sine squared theta, and immediately I'll factorize that because cos squared plus sine squared equals 1, so that will all disappear to give a squared minus 2a squared cos theta plus a squared, so we've got 2a squared minus 2a squared cos theta, but we need to combine this into one term and have a theta over 2 and a sine squared, not a cos. So to do that, we're going to use the identity that sine, let me use x, sine squared x is equal to a half minus a half cos 2x. So if I multiply everything by 4, 2 minus 2 cos 2x, and let x equal theta over 2, then this is 2 cos theta, and this will be sine squared theta over 2 with a 4 in front. Now I've got a's, but I can easily factorize that out to make this match what I've written there. So dx by d theta squared plus dy by d theta squared is equal to a squared times 4 sine squared theta over 2, which is what we need, where k is 4. Let me just finish it off by writing it exactly as I've got it. K is equal to 4. Part B, the part of the curve from theta equals 0 to pi by 2 is rotated through 2 pi radians about the x-axis. Determine the area of the surface generated, giving your answer in terms of pi and a. Okay, this is another formula that is given in your formula booklet. So it's the parametric form about the x-axis, and that is 2 pi, the interval from 0 to 2 pi, of y times the square root of dx by d theta, or dt I think in the formula booklet, plus dy by d theta squared with respect to theta. Now this thing inside the square root, we've done that in part A, it's right there, 4a squared sine squared theta over 2, and y is equal to a1 minus cos theta. And then we've got the square root of 4a squared sine squared theta over 2, 2 pi in front, 0 to 2 pi. Now when we square root that, we're going to have 2a, and we've got another a there. Let me pull both of those things out to make a 4a squared pi in front. They're all constants. So we've got 1 minus cos theta here, and we've still got sine theta over 2 when we square root that. Okay, that's still not going to integrate yet very nicely. We've got sine theta over 2, that's okay. We've got minus cos theta sine theta over 2, that is not okay. So what we're going to do here, we need to change that theta into a theta by 2 so that the arguments match. And instead of changing it into a sine squared, because that's going to interact with the sine to make a sine cubed, not so easy to integrate, but if we change it into a cos squared, then the sine theta by 2 will be the derivative of the cos theta by 2 squared, and we'll have a bracketed thing multiplied by its own derivative, which we know how to integrate. So using cos squared x is equal to a half plus a half cos 2x. Rearrange this a little bit. So we get cos 2x there, and then instead of x, let's have theta over 2, and that is equal to cos theta. So that has the same argument and is the right trig function to help us integrate. So that 0 to 2 pi seems like a long integration, this one. Minus 2 cos squared theta by 2 minus 1 times sine of theta by 2. Expanding that out. I had hopes that maybe that sine theta by 2 would cancel, but it will not, it will add together. So we're going to have 2 sine theta by 2's and a minus 2 cos squared theta by 2 times sine theta by 2. But I think finally we are ready to integrate. So the first term, actually let me just get rid of that 2, pull that out as well. I don't have too many constants floating around. So the first one will integrate directly, and that will give us minus 2 cos theta by 2. And this one, if I just change slightly how I've written that, put that in the big brackets there, then that might make it easier to see why I know this has come from something like this. Now if you differentiate this term, you get 3 times cos theta by 2, so we need a third in front there. But then you also have to multiply by the derivative of the thing inside the brackets, which is a minus sign, so actually that change that back to a plus, minus sine theta over 2 times by the derivative of that argument, so we need a 2 in front. So we don't actually have this. I'm just working that through in my mind as we differentiate this bracket here, what we would get, so that we match with what we've got in the interval. So saying it quickly again, the 3 here would come down, cancel with this 3, that would leave a 2 behind. That's this. The bracket itself doesn't change, but then you multiply by the derivative of this, which is a minus sine theta by 2 times by a half, and that half will cancel with this 2. So that I think is correct. Now we can do 0 to 2 pi here and evaluate. And that's quite nice because as we put 2 pi in, we're going to divide it by 2 in both of these terms, which gives us cosine of pi, which is minus 1, and cosine of 0 is 1. So either we're getting 1 or minus 1 out of these cosine terms. So we've got equals 8a squared pi. So that's a minus 2 times minus 1, 2. Minus 1 cubed is still minus 1, so that's minus 2/3. Minus 2 times a 1 minus 2, and 1 cubed plus 2/3, which is 8 over 3, and we're multiplying that by 8a squared pi, which gives us 64a squared pi over 3, and that should be our surface of revolution. got it in terms of a and pi. Okay, there we go, question 6 finished. On to question 7. Plane equations. So we've got the equation given to us here of capital pi. Determine a vector perpendicular to capital pi. Okay, that's a cross product because we've got two direction vectors inside the plane that are non-parallel. So a perpendicular vector to both of those is perpendicular to the plane. So we do 0, 3 minus 2, cross that with 1, 1, 2. And I think this also is given to you in your formula booklet if you forget how to do the cross product. So we've got 6 minus 2. And then for the middle element, minus 2 minus 0. And the last one, 0 minus 3. So that gives 8 minus 2 minus 3. And that is part A already finished. The line L meets pi at the point 1, 2, 3 and passes through the point 1, 0, 1. Determine the size of the acute angle between pi and L. Give your answer to the nearest degree. Okay, so we've got a plane, there's pi, and we've got L meeting the plane at point 1, 2, 3. Say it looks like this, and that also passes through the point 1, 0, 1, and the normal of the plane here is what we just found in A, that's 8 minus 2 minus 3. The angle we want is this angle here, we call that theta. L, let's find L. The direction vector of L is going to be 1, 2, 3, minus a 1, 0, 1, 0, 2, 2. Now we've got the direction vector of L and the normal of pi, we can do the dot product. So if we do 8 minus 2 minus 3 dot 0, 2, 2, that has to equal the magnitude of the first one times the magnitude of the second one times the cosine of the angle between them. So we get 0 minus 4 minus 6, the square root of 77 times the square root of 8 cosine theta. So cosine theta is equal to minus 10 over the square root of 616. I won't worry about simplifying that because we're about to do the inverse cosine of it. Minus 10 over root 616. After changing my calculator into degrees mode, that gives me 113.76 dot dot dot, and I won't round it yet because we're not quite finished. We want the acute angle between pi and L, labelled as theta on, oh dear, labelled as theta on the diagram. Let me change all of these into something different. That's not a theta. Let's call that alpha. So alpha is this obtuse angle. So 180 minus that gives me this angle here as 66.23 dot dot dot. But that's still not the acute angle between L and the plane. That's the acute angle between L and the normal of the plane. So to get theta from there, I now need to do 90 minus that. And that gives me 23.76. Now I can round to the nearest degree, 24 to the nearest degree. For theta, now theta matches my diagram, this one in here. Part B finished. Part C, determine the shortest distance between pi and the point 6 minus 3 minus 6. So again, we've got our plane, and here's a point 6 minus 3 minus 6, and we know the normal of the plane is still 8 minus 2 minus 3. So we've got a few different ways you could do this, and usually what I would do is parallel planes. Find a plane parallel to this plane, i.e. with the same normal, that contains this point, and then find the distance. But just to mix it up a little bit, let's do projection, because we know a point on the plane as well is 1, 2, 3? 1, 2, 3. So we can get this vector here, or the direction vector, 6 minus 3 minus 6, minus 1, 2, 3. So that's 5 minus 5 minus 9. So if we project that onto the direction of the normal, that will give us the perpendicular distance, i.e. the shortest distance between the point and the plane. So if we do, let me just write a dot b over the magnitude of b. This is the projection formula, so you're projecting a in the direction of b. So what we're doing here is 5 minus 5 minus 9 in the direction of 8 minus 2 minus 3, so we have to divide it by the square root of that. So that's 40 plus 10 plus 27 over the square root of 77. And that gives 50, 67, 77 over the square root of 77. How suspicious. Square root of 77, and that is the shortest distance between the point and the plane. Different ways of doing it, different ways that I would normally do it, in fact, but this is one of the options. That is the question finished. On to question 8. Here we're given in is equal to the integral of cos power nx. Prove that for n is greater than 2, this formula holds. So usually with these sorts of questions we're doing integration by parts, but of course to have integration by parts you need 2 parts in your integral. So the first thing I'm going to do is split this into a cos n minus 1x times cos x. The reason I think that particular split is going to be useful is because I can integrate cos, and that will give me a sine, and then in my by parts formula I'll be multiplying the sine by the derivative of this part here, and when I've got cos to the power of something times by a sine, as we used earlier in the paper, that's a bracketed function multiplied by its own derivative, and we can integrate that fairly easily. So that's where I'm going with this. We're going to call this one v prime, and this one u in the by parts formula. So we've got uv minus the integral of v u prime. So in is equal to u, which is cosine n minus 1x, and if I put on the side here the integral of cos x is equal to sine x, so this is multiplied by sine x, minus the integral of v, which is the sine x we just found, times the derivative of cos to the power n minus 1x, which is n minus 1 cos to the power n minus 2x multiplied by the derivative of the thing in the brackets, although I didn't actually put brackets around it, but that is going to give us a minus sine x. Now it has not worked out how I expected, but it is going to work out nonetheless. We're going to have a sine times a sine, that will be a sine squared. We can change that back into a 1 minus cos squared, and that will interact with the cos to the power n minus 2 in a good way. So I'm not put off, even though it didn't quite go how I was expecting when I started. So this is changed to a plus with that minus there. Sine squared x. No, let me bring the n minus 1 out. Sine squared x cos to the n minus 2x. And then we can change that sine squared into 1 minus cos squared times by this. All the rest is still the same. Now that's good because when we multiply this out, we get cos to the power n minus 2x, which I assume we've got an I2, yes, I to the n minus 2. That's what that will become. And then cos squared times cos to the power n minus 2 just becomes cos to the n. And that's okay because that's in, and we can have that interact with in on the left-hand side. That's probably where this divide by n will come from. So let me fill in what I've missed off. So now I'm going to rewrite this in terms of i's. So we've got n plus 1 times in minus 2 minus n plus 1 times in. And that becomes minus n times in plus in. And the plus in will cancel with the one on the left hand side. I'll leave that in brackets because I think we need that like that in the final expression. We bring the nin onto the left. Plus n plus 1 I to the n minus 2, and then divide everything by n. Missing an x, plus n plus 1 over n I n minus 2. Let's just check that matches. Don't need all these circles everywhere. I to the n 1 over n cos to the n minus 1 sine x, yes. And n minus 1 over n I2. No, I've changed my minus 1 into a plus 1 for some reason. And made a second mistake when I was doing that to end up with the right thing. I was being so enthusiastic, I knew those in's were going to cancel. So we had a minus nin minus, with the minus as a plus. Yes. And this is all minus. Okay. Always worth double checking what you finish with matches what they want you to finish with. Now it does. Part B, show that for positive even integers n. Why do I get the feeling I'm not going to like this question? How are we going to show this? I think let's start by just putting in some numbers. So going from 0 to pi by 2. Of cosine to the n x dx I n, which equals 1 over n cos to the n minus 1 x sine x plus n minus 1 over n I to the n minus 2. Okay, we knew all of this. Now let's put in, they are even, so let's start with 2. I2 is equal to 1 over 2 cos to the 1x sine x plus 2 minus 1 is 1 over 2 I0. Now let's take a moment here and evaluate I0. I0 is from 0 to pi by 2 of cosine to the 0x, which is just the integral of dx. 0 to pi by 2, which is x from 0 to pi by 2, which is pi by 2. So I0 is pi by 2. Okay, now we know that. Let's go a step further. Let's go I4, which is 1 over 4 cos cubed x sine x plus 3 over 4 I2, but we know I2 is a half cos x sine x plus 1 over 2 I0. Now we know I0 evaluated, but I haven't evaluated the rest. So let's leave that for now like that. Not really seeing... Let's try putting in... Let's start from the other end. I don't like these questions because when it says show, I'm not really sure exactly what steps the examiner is looking for. And there's no point just getting to the solution because the solution is given to you in the question. So let's try IN. And that's 1 over n cos n minus 1 x sine x plus n minus 1 over n of in minus 2. Now let's do in minus 2. That's 1 over n minus 2 times cos of n minus 3 sine x plus n minus 2 minus 1 is n minus 3 over n minus 2 of in minus 4. So that's 1 over n minus 4 cosine n minus 5x sine x plus n minus 5 over n minus 4, and then another bracket, dot dot dot. Okay, I'm seeing some of the things that we need. We've got some n minus 2s, n minus 4s in the denominators. We've got n minus 1, n minus 3, n minus 5 in the numerator. We've all got an awful lot of sines and cosines floating around. So dot 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 to this expression up here. But all of these are in brackets as well. We've got brackets piled up to everywhere. There's all sorts of brackets going in here. No, we haven't evaluated. Okay, this is where it's going to help. So we're doing all of this from 0 to pi by 2. Yes, okay. I can see where we're going. Because cosine of pi by 2 is a 0. And sine of 0 is a 0. And we've got a cosine and a sine in almost every term. So when we evaluate this, one of those two multiplying factors is going to be a 0. So when we evaluate this, all of these, they're all going to become zeros. Everything is going to become a 0 except for this last term here, which is going to become a pi by 2 on the higher limit and a 0 on the lower limit. Sorry, not that half in front, just this I0. But because of this nested bracket up to the nth degree, we've got all of the multiplying factors as well. Every multiplying factor in front of the bracket is going to apply to that final term I0, except for this leading term up here. That's not going to influence I0. So we are, I'm just going to assume that's enough. We are going to get n minus 1 over n times n minus 3 over n minus 2 times n minus 5 over n minus 4 times 3 over 4 times 1 over 2 times pi by 2. Was that enough? 3 over 4 and a 5 over 6 as well. Okay, putting that all together. and then we've got n minus 2, n minus 4, 6, 4, 2 times pi by 2, which I think is how they wanted it written. Yes. So from 0 to pi by 2 of cos to the n x dx, we have this. Okay, not the nicest question, I would say, but I think we're there, probably with enough working to satisfy the examiner. Hence, determine the exact value of this. Cosine power 6 sine squared. So the integral from 0 to pi by 2, cosine power 6 times sine squared. Now that does not match what we've got. We want a cosine power something. So straight away, let's change that into a 1 minus cosine squared. So we're going to get two terms. Zero to pi by 2 of cosine power 6 minus 0 to pi by 2 of cosine power 8. And I've split them just to make it really clear that that becomes I6 minus I8. And then we can evaluate using the expression at the top of the screen for 6 and 8. So 6 is 5 times 3 times 1, 6 times 4 times 2 times pi by 2, minus 7 times 5 times 3 times 1 over 8 times 6 times 4 times 2 times pi by 2. Putting all of that on a calculator gives me 5 pi by 256. Part C finished. Just double check. Exact value, yes, finished. On to question 9. The ellipse E has equation this. The foci of E are F1 and F2. Determine the coordinates of F1 and F2. So if we've got x squared over 9 plus y squared equals 1, then A is equal to 3, B is equal to 1. For the coordinates, we want E as well. B squared is equal to A squared 1 minus E squared. Comes out of the formula booklet, again in the conics section. So we can do 1 is equal to 9, 1 minus E squared, 1 over 9 is equal to 1 minus E squared is equal to 1 minus 1 over 9, 8 over 9, so E is equal to 2 root 2 over 3. Now E itself is a positive number, but when we get the coordinates of F1 and F2, we're using plus or minus AE0, where we know A is 3, 2 root 2 over 3, 2 root 2. So F1, 2 root 2, 0, and F2, minus 2 root 2, 0. These are the coordinates of the two focus points. Write down the equation of each of the directrices of E. Again, as I mentioned earlier, this is in your formula booklet. If you forget, x is equal to plus or minus A over E. And we know A is 3, we just found E is 2 root 2 over 3, which gives us plus or minus 9 root 2 over 4. We've got our two directrices there. The point P lies on the ellipse. Show that PF1 plus PF2, so the distance from the point on the ellipse to the two different foci, when you add them together, must equal 6. So this is going back to basic definitions of what an ellipse is. We can try not to draw it too terribly. fairly terrible. So what we've got is a focus point here, a focus point here, but we've also got the directrices. Here, this is x is equal to 9 root 2 over 4, and over here, x is equal to minus 9 root 2 over 4. We know the focus is 2 root 2 and minus 2 root 2. So if we take any random point P on the ellipse, say here, Pxy, then they're asking for this distance here plus this distance here. But what's really useful in this situation is to remember that that distance here, let's call this d, from P to D, that is connected by definition of the ellipse from P to F1 here. P F1 is equal to E times PD. Now I'm going to have a D on the other side, so let's call that D1. And it's the same over here with this one. Let's call this D2, and this is F2. So PF2 is equal to E times PD2. And we're talking about the distances here. Now when we come to doing PF1 plus PF2, we're going to change that into E times PD1 plus E times PD2, because D1 I can find out fairly easily because we know where that directrix is, and we know up to the focus point that that is a fixed distance, that never changes. And then all I have to do to get the distance PD is to add on that little bit here. Actually, it doesn't make sense to do it that way at all. What I'm actually going to do is take this distance here on the x-axis of the directrix and subtract the distance x here. That makes far more sense. So PD1, we've got E times the directrix, 9 root 2 over 4 minus x. PD2, remember this is a distance, so thinking about it in terms of that x again here, is just this full distance. So that's the full distance from D2 to the origin, that's 9 root 2 over 4, plus that little bit x. And we know what E is, if I go back, I've forgotten already, 2 root 2 over 3, so that's 2 root 2 over 3 times 9 root 2 over 4 minus 2 root 2 over 3 times x plus 2 root 2 over 3 times 9 root 2 over 4 plus 2 root 2 over 3 times x. And what you'll find is that it's not dependent on x. Simplifying these roots and fractions, we just get 3 plus 3, which gives us the result required, that these two equal 6. Part C, the straight line through P with equation y equals 2x plus c meets E again at the point Q. The midpoint of PQ is M. Show that as P varies, the locus of M is a straight line passing through the origin. Okay, let me try and visualize what's going on here. Here's our ellipse, kind of. Pretend that that is an ellipse. Oh dear. Yes, you can use your imagination here. So if we take a random point again, P, the line with gradient 2, sort of something like that, cutting here at C, cuts the ellipse again at Q, and the midpoint of that is M. So as P comes around the ellipse here, the gradient of this line is not going to change. So it'll go something like that. And then we've got P here, P prime, Q prime, and then M prime. And you can see that M is going a little bit down as p comes round, and eventually there'll be a tangent point here, and they're telling us it goes through the origin, so there's a line here where p and q, the midpoint, must go through the origin, and then you can see that it will come up as it goes to the left. So the line of M is a very shallow looking gradient like this, but it didn't say sketch it out nicely on a graph. I don't know, can I call that a nice sketch? What it said was, show that as p varies, it's a straight line passing through the origin. So what we're going to do is find the coordinates of p, the coordinates of q, use those to find the midpoint, and show that the midpoint xy coordinates, I'll call them capital X, capital Y, show that they give a straight line. To do that, I need the original equation, x squared plus 9y squared is equal to 9, and we're combining that with the slightly more generic 2x plus c. So y squared is equal to 4x squared plus 4xc plus c squared. Substitute that into the ellipse equation. It's 9 lots of this, so that's 36x squared plus 36xc plus 9c squared equals 9. Now we're solving this to find the coordinate of x, the coordinate of intersection. So we've got 37x squared plus 36cx plus 9c squared minus 9 is equal to 0. So our quadratic formula, minus 36c plus or minus the square root of 36c squared minus 4 times 37 times 9c squared minus 9, and don't panic despite how horrendous that looks, divided by 2 times a 37. Now I'm not panicking, although I might have done if I'd just come to that without having done a similar question not too long ago, because I know when we find the midpoint we're going to be using these two solutions. We've got two solutions because of the plus minus. One of those solutions is p and one is q. And what we want to do with those is find the midpoint. So instead of worrying about evaluating that square root, I'm just going to find the midpoint, the x-coordinate of m, which I know is x1 plus x2, and as soon as I do that, those opposing plus square root and negative square root will cancel each other out. So that, if I make it a little bit clearer, is plus square root of that thing divided by 74 plus minus 36c minus the square root of that thing divided by 74, all divided by 2. So as we put this over a common denominator of 74, I hope it's clear that that cancels with that, and we get minus 72 over 74 divided by 2, which is minus 36, sorry, missing a c, 36 over 74, which simplifies further to minus 18c over 37. So that's the x-coordinate of the midpoint m. And now we know also that m must lie on this line, y is equal to 2x plus c, so we can find the y-coordinate of m by doing 2 times the x-coordinate plus c, putting this in here, minus 36c over 37 plus c is c over 37. So my coordinates of m, depending on c, minus 18 over 37 lots of c, and 1 over 37 lots of c. Now if I call this capital X, just to distinguish it from x's previously in the question, capital Y, then we can see that there's a very obvious connection between these two. X is just minus 18 times y. And if I rearrange that, we see the line equation coming through. So that's a straight line through the origin. And minus 1 over 18 matches our very shallow gradient that we had on our kind of okay looking sketch, and it definitely goes through the origin because there's no constant here. So that is the final part, I think. Again, double check, make sure you finish all these questions off. Part C, the locus, yes. So part B was that, and this is part C. And final part of the final question. So some interesting questions in that paper. I didn't really like the matrix one, and I'm not too fussed about the show part of the previous question, question 8. But this last one was fairly standard, and I hope that going through it all has really helped you out.